Okay, gang, I understand you're involved in a Mars planning mission and a lot of different components, obviously, going into landing 25 tons. A lot to think about, but one thing that you may not realize the importance of is a spacesuit. Without a spacesuit, you ain't going anywhere. And you might think that this is a trivial thing because after all, we have a lot of spacesuits out there, a lot of history in spacesuits. But when it comes to Mars, the answer to that is no, we have literally nothing. So I'm going to take you through why we have literally nothing. I'm going to take you through where spacesuits stand today, why they're Mars, what it's going to take to make them work, and how they can come back and change the world today that we live in. So that's a lot to talk about. And usually this talk takes about an hour and a half. So I'm going to go through some of these slides rather quickly, just because I want to give you a smattering of what's involved. So let's just start with this. The current gold standard on the moon or anything beyond low Earth orbit is, of course, the Apollo spacesuit. So let me go back to what happened there. Somebody interrupted. So here we go. So I don't know if you can hear this. This is Buzz Aldrin descending the ladder of the moon.
You do have to be rather careful to keep track of where your center of mass is. Sometimes it takes about 2 or 3 phases to make sure that
now what Buzz is doing here is he's in the limit of this Apollo EMU, testing the limits there. Inside, I was on console at mission control during all of this, so heard every word and got a pretty good feel for what was going on. Because of the high center of gravity and the extreme and a lot of other factors, this suit was barely adequate, but was okay for the purpose that it was designed. Well, I wanted to show you that. And then I wanted to say that if you're going to design a future suit, that's the gold standard right now because it's the only suit that's been to the moon. So the question for Artemis, which is the lunar program that's supposed to be launched in 2025, 2026 on the gigantic SLS rocket, maybe even Starship, is can you do better than that? And can you do it faster? And can you do it cheaper? These are key questions. And that's what's gone into all the hubbub that you might have read about spacesuit problems getting ready for the Artemis program. So I wanted to talk to you about the technologies involved in these spacesuits. That they fall into 2 major types of suits. One is pressurized by gas, and the other one is pressurized by fabric, mechanical counterpressure. And maybe some others will come along that are radically different. But the 2 up top are the main ones in the game right now. So I'll take you through a historical perspective. These are what NASA spacesuits have looked like since Apollo. And if you go counterclockwise from the Apollo EMU through the Heart suit and different versions of the suit and come down and you see rear entry suit port. NASA had a spacesuit called the Z2. This is where everything has gone configuration. We don't know what the Artemis suit is going to look like, but this is what it has to build on. And let's see, go back. So then you talk about mechanical counterpressure suits. These are first design was in 1967. It used fabric to actually pressurize the body instead of gas. Been around a long time, and the latest incarnation of that is by our old friend David Newman at MIT. And here you see David modeling her mechanical counterpressure biosuit. So this uses spandex, Kevlar, elastic, urethane foam. It has been tested to 3.6 psi, but it's very difficult to get in and out of. It's very difficult to cool. It has to interface with gas-filled gloves and boots, and it has been funded in some characteristics, but not baseline by NASA. And also, it does not have a life support system. important to add that. There's no life support system in the biosuit. So when you talk about designing a suit, there are three things that you really have to put at the top of the list. One is the mass of where you're going, the gravity level, and the inertia. Those are the holy grail of spacesuit design. And the bottom line is, you can't, speaking to geologists and military personnel, you can't expect to do useful work for any length of time if you have any more than the equivalent. Equivalent is an important word, of 23 kilograms or 50 pounds as a spacesuit. Just to put that in perspective, 50 pounds on the moon with 1/6 gravity is equivalent to 300 pounds on Earth. And that's about where all those spacesuits come in at. They come out at about 300 pounds. So the limit, you know, when you're walking around on the moon, even the new one, Artemis suit, will probably be equivalent to 50 pounds that you have to move around. And if you ever tried to move around with a backpack that's 50 pounds, you get an idea. So, of course, that's not the only, the challenge is obvious. And there's a lot of different, let me take you to some other things. Besides the mass, there's how do you get rid of radiation? How do you get rid of, how about glove dexterity and walking mobility? How about micrometeorite protection and real-time help, emergency oxygen, getting rid of waste management, body temperature regulation, battery limits? These are all factors that have to be considered when you design a spacesuit. So there's a huge number of things that have to be rolled into that. So mass and gravity aren't the only thing, just wanted to let you know. It's an obvious and very difficult challenge. And I tell you right away, you might have seen pictures of spacesuits in the news, and they look cool, but don't be fooled because they look pretty. For instance, the Boeing Starliner suit that's been designed and is waiting to be used by Boeing on Starliner is not an EVA suit. It's internal, inside the capsule. The MIT biosuit does not have a life support system. The cool-looking SpaceX Dragon suits that you've seen, they're intravehicular, they're not extravehicular. And at the bottom, you see NASA's version of the XEMU, which was $1 billion over budget and was canceled. And a new RFP was put out for a brand new version, which the award has just been given to Collins Engineering. And by the way, Collins has been working with the NASA XEMU for several years. So it's reasonable to expect it's going to look something like that. Here are the players in all these spacesuit designs. There's NASA, there's Collins, or used to be Hamilton, or ILC, Boeing, SpaceX, Paragon, Oceaneering, David Clark. These are all players. All of them bid on the Artemis lunar suit, but the contract was given to Collins, up number 2 there. And they had several subcontractors, which I won't get in right now. So that's who that's who is working on the lunar suit. You got to remember, though, something you probably heard before: those who ignore history are doomed to repeat it. So you have to make sure you don't repeat the mistakes of the past. And this is especially true when it comes to Mars. So I'm going to talk to you now about a spacesuit for Mars. Can you use any of these spacesuits that we looked at? And the answer, well, the first question is, why even think about it? It's a long way away. Maybe, maybe we're not going to be there for 10 years. But it takes a decade to create, develop, test, and qualify an EVA spacesuit anywhere you go for Mars. So the target date for humans to Mars that's been bandied about is mid-2030s. That means mid-2020s, you better start building a spacesuit for Mars. So the clock has already started. If you are going to want to use a lunar suit, an Artemis suit on Mars, you better understand the difference between the moon and Mars. And there's a lot of differences, starting with the gravity. Gravity on Mars is 38% of Earth. The moon is 16% of Earth. So already you look at that and you see that the gravity level is almost twice, more than twice what it is on Mars, which means a spacesuit that weighs 50 pounds on the moon will weigh over 100 pounds on Mars. Ain't gonna work. The other things that are different is Mars has an atmosphere of carbon dioxide. The temperatures are much more benign. On the moon, if you face the sun, you're looking at 123 degrees Celsius. And if you face away from the sun, you're looking at 247 degrees below zero. On Mars, it's much closer to Antarctica. 22 degrees, which is almost 80 degrees at the equator, minus 73 at night. Soil on Mars is much more like Earth. It's not like that on the moon. You can probably grow plants, everything. 44% of solar reaches Mars, much more solar reaches the moon. The radiation issues, the seasons. So anyway, the point of it is, and also there's a much more significant radiation risk on Mars than there is on the moon. So with all these things to keep in mind, if you try to use an Artemis suit on Mars, the answer is going to be no. The temperatures it's going to be far too heavy. The radiation environment is completely different. Mars have an atmosphere. The gravity is different. The soil is different. The portable life support system, which depends on a vacuum on the moon, won't work on Mars. Yada, yada, yada. It goes on and on and on. So what do you do? I've left out the most important part. We have a lot of pressure to conform to something called the 1967 Outer Space Treaty to provide planetary protection. It is now a key requirement in human Mars missions. There is not a spacesuit designed yet that considers planetary protection. So you need to start with a completely different sheet of paper, because unless you do that, the spacesuit you have on Mars might look like this, or it might look like this. It'll probably look like this if you have to deal with an Artemis suit. You're tethered to a rover. You can't go anywhere. So I like to say this is it's not a fashion show. This is a serious problem. If you expect to do any useful work, build things, discover things, and live and work on Mars. So given those concerns, what can you do? What do you do? And the first thing that comes to mind is that recognize that Mars is a planet. It's a big place. It's not low Earth orbit. It's not the moon. It is a planet. So what does that mean? I want to show you the difference. Just a quick commentary of what astronauts commented when they first went to the moon. So listen carefully. This is Apollo 8.
Christmas up here, doing experiments, taking pictures, and firing our spacecraft engines to maneuver around. What we'll do now is follow the trail that we've been following all day and take you on through to a lunar sunset. The moon is a vast, lonely, forbidding type existence or expanse of nothing. It looks rather like clouds and clouds of pumice stone. And it certainly would not be a very inviting place to live or work.
Buzz Aldrin capsulized it. Look at this wonderful photo. Magnificent desolation. This is what the moon is. This is where Artemis is going. Contrast this with Mars. Here are just some photos of Mars. You've probably seen some of these. Here's Viking 2 widespread frost. This is water frost on the surface at Utopia Planitia. Here you see ice-filled craters more than 50 miles across. That's ice. You know what you can do with ice, of course. You can use it for drinking. You can use it to make oxygen. You can use it to make rocket fuel, lots of things. See these dark streaks near the equator at the top of this crater? This is evidence of recent running water that's burst through the surface. Here you see some really interesting photos. The left top one, water ice cap at the North Pole, limestone deposits in the floor of Gale crater, dunes and ripples, just magnificent stuff. Here's limestone deposits poking through CO2 ice at the South Pole, rocky terrain, undulating plains, just hills and valleys, majestic craters, rock-strewn plateaus, winds and dust, and dust devils, probably, if we haven't seen it yet, we probably will one day catch flowing liquid water. So summarizing, it looks like you've got this environment, so why not start with a fresh sheet of paper, keeping that in mind if you can design a spacesuit for Mars. Keep in mind, in the past, engineering dictated the design of a spacesuit. Science was the slave. That's the past. That was Apollo and the shuttle, ISS, and it's probably going to be Artemis. When it comes to Mars, it must be the other way around. Science has to be in control of engineering and the design of a suit. So a number of years ago, we started a project here at UC Berkeley called the Mars Suit Project. The goal was to develop and build a spacesuit for Mars using the Martian environment and leveraging STEM or STEAM resources with something called the Hypernet paradigm. I'm going to show you what that is, because it's useful for all kinds of things. It's going to be useful for your projects if you take it into account. So this is the way the Hypernet paradigm works. You take a big project, in this particular case, a Mars spacesuit, and you break it into pieces, elements. And here you see elements: pressurization, thermal control, materials, utilizing resources, Mars science, sizing, life sciences, power system, blah, blah, blah. There's about 11 or 12 of these. The next thing you do is you combine them or simplify them, work packages. So these are combined into 1, 2, 3, 4, 5, 6 packages, 7 packages. You see them. Now here's where the thing actually starts to work. You then form an organization. And here in the dark red, you see these work packages that they're shown horizontally: pressurization in 1, 2, 3, 4, 5, 6. You then recruit talent pools from all over the place, from universities, from the public, from the world. And you ask people, would they like to join a team involved with each one of these projects? So here you see just a hypothetical. Pressurization and thermal control would be MIT with a minority partner one, and helmet torso, sorry about that, would be another team. And then the life sciences would be the Naval Academy, Johns Hopkins High Schools, and another team. And the idea is you're getting people who are passionate about the subheadings, and they're part of a team. So the way this works, you give the teams a starting point. They don't know much about this when it starts, and you tell them, do your research. We're going to give you some basics like I'm giving you guys now, and come up with a report. Come up with a report and do a trade study and study it, and then come up with this report. So at the report, at the end of a period of time, like a semester, you follow that line at the bottom, goes reports to feedback. It goes into a peer review group, and that peer review group gives it a reality check and makes it more realistic, because when you first start out, you don't know the limitations. Then what happens, it comes back into the hopper to the second team, the second semester, who start with that, and they take that and evolve it. And then it does it again. So what you're talking about is an iterative, evolving approach over time that keeps on maturing the initial design. And the teams are consistent, and the people joining the teams can do it either in high school or college. They can use it for a graduate degree. They can use it for jobs. And by the way, if you think about this model, it can be used for a lot of things. It can be used for design a Mars mission, not just a spacesuit. It can be used to study cancer. And that's a whole other talk, but I just want to introduce you to that, because that's what led to the designs. So over a period of years, the design that evolved, and you're going to look at an initial prototype. This is just it's not a functional prototype. It's just an appearance prototype of what components are needed. So this was built just so we knew what the parts were that were going to go into a Mars spacesuit. And then following that, the following design came about, and it's very, very radical. So what it is it's really 2 spacesuits in one. The helmet is completely separated from the torso. And let me explain why that's so important, because if you separate the helmet from the torso, you're able to actually pressurize this spacesuit from the outside. You can have compressors or pumps as part of the spacesuit that's pumping the Mars atmosphere into the torso to pressurize the torso. And then it goes out a relief valve. And it's completely separate from the helmet. So what's the advantage of doing it this way? It's called an open loop design. And the big advantage of doing it is that that atmosphere of Mars is cool and dry. It can remove heat, sweat, toxins, contaminants. And by blowing it in and then blowing it out, you don't have to have fans and pumps and heat exchangers and big batteries and all of the stuff that makes an Artemis spacesuit 300 pounds. In fact, you can make this so lightweight that you can get it down to, the latest is 125 pounds. So if you get it down to 125 pounds complete, that's more like it. Now you can walk around on Mars because it's less than 50 pounds on your back to do all this work. And there are a lot of other advantages of doing this. Let me show you some of the advantages that come. Well, right off the bat, you can almost guess if you have a puncture in a suit like this. In normal suits, like in the Artemis suit, all the air in that suit is voided almost immediately, and you're going to be dead in about 10 or 15 seconds because the oxygen that you're breathing is also connected to the torso. All of it goes out. In this case, the helmet is separated by a neck dam, a special material neck dam that separates the two components. So if you get a puncture anywhere in that suit, the only thing you're losing is the same CO2 that you pumped in. And you're buying time. Now you can fix the puncture. Instead of seconds, you have minutes and to actually take corrective action. So that's the other advantage. The third advantage is the biggie. I talked about it before, planetary protection. Here you see a picture of an Apollo 12 spacesuit that's literally dumping everything inside that spacesuit out onto the moon. It's contaminating the lunar surface. Every spacesuit has been designed just like this. We have done nothing to prevent this contamination or to prevent the contamination that could come back. So the design that we have evolved actually makes use of the fact that we're blowing the atmosphere in and blowing the atmosphere out. It enables you to put bacterial viral filters at the compressor inlet and at the relief valve outlet to stop anything bigger than a micron from getting in or out of that suit. Just to keep that in perspective, a coronavirus, individual coronavirus is 1.25, 1.5 microns. These filters will stop that coronavirus and anything of that size. Also, you have to take toxicity protection. So we use a dense monolithic membrane to prevent the toxicity. That goes against the skin. The suit is going to be very, very lightweight. So for instance, on Apollo, let me show you if I can. I guess I can't, but maybe I can. Yeah. Here's what happens when you have a bad center of gravity from too heavy a spacesuit. Now, here's what happens when you lower the center of gravity by basically putting more mass forward. So here are these kind of 260
we stir up darker
that
material,
effectively lowers the center of
just
gravity
slightly, but it's darker.
much better
The
able
same
to
old
walk.
thing.
That's what happens when you do
That's
that.
right.
Also, another advantage in this design that we have is a variable pressure glove because you get a lot of injuries in fingernails. So by lowering the pressure in the glove for work that requires dexterity, you reduce the injury. So there's lots of things like this to take into account. Advanced thermal control. I can't get into all of these. Ceramic textiles. All these are part of the design that came through. But I would like to talk about one, which is how you get help in an emergency. Now, on the moon, you've got mission control because you're only about a minute away by audio or video, because that's how long it takes for the signals to go from Earth to the moon. Now, on Mars, you're talking 40 minutes. It's too long to get help. So the suit has to replace mission control. So one of the designs we have, I'll show you right here, being tested at the Johnson Space Center. Let me find it.
inlet temperature check.
Your LCBG inlet temp is 37 degrees Fahrenheit, and the optimum is 56. You might consider adjusting your coolant to match.
Actually talking to Chris while he works. He's asking, and if he needs help, like how long is it going to take me to get back to the habitat before my oxygen runs out? It can tell him, and it will also tell him how fast he has to move, if he has to walk faster or slower, all kinds of things like that. So you need that. Well, so far what you've seen is just PowerPoint stuff. So the real question is a big difference, of course, between talking and reality. So I want to show you where this has gone in the last year and a half. What you're looking at is the first functional Mars spacesuit ever built. And this spacesuit separates the helmet from the torso. And let me show you the helmet. The torso is being pressurized by carbon dioxide, 95% of the Mars atmosphere. And the helmet is being pressurized by oxygen. The suit is going to weigh, this suit weighs about 75 pounds. When you add communication, a buddy system, battery, and everything else, the projected weight is going to be about 110 to 120 pounds, not 300. And that makes it easy. And this one, not 3/8, not 38. You're seeing him, you're about to see him work or take us through his paces. And you see he's walking pretty much, I don't want to spend too much time in this, but let it be said that this is a much easier suit to work on, and it's going to weigh a lot less than this on Mars. So this is what you have to do. Now, I'd like to just digress for a minute that the design of that suit has been used, believe it or not, to design another suit that could help stop a more serious pandemic than COVID. So first, what's a pandemic? It's a rapidly spreading pathogen capable of unknown origin, potentially fatal. It can cross domestic and international and intergalactic boundaries. How the virus gets in and out is poorly understood, but it can go both forward and back direction. And there you go. So that's the definition of a pandemic. The space community has to be involved in one way or another, because you're looking at Article 11 of the 1967 Outer Space Treaty declaring avoid harmful contamination resulting from the introduction of extraterrestrial matter. So whatever you're doing and planning on Mars for your Mars mission, you must take this into account. Forward contamination control for all outbound missions, backward contamination control for anything that you do that's going to come back. Not just a spacesuit, but any piece of equipment that you're going to touch. You must take this into account. So forward contamination control, you're looking at Perseverance undergoing sterilization in a clean room prior to launch. This is the kind of thing that you do. And backward contamination, the only example we have of any serious note was Apollo, where there was a concern that moon bugs might exist. And how do you stop them from being released? And so there was an attempt to stop any potential moon bugs from getting back from the moon, if they existed, to cause some kind of horrible pathogenic contamination on Earth. And the way it was done was to try to stop it. It was not done trying to stop it at its origin. It was trying to stop it once the command module landed. So there was what we call a chain of protection. There was filters in the post-landing ventilation system, the command module, or biological isolation garments, or mobile quarantine facilities. Astronauts were quarantined for 14 days in the Lunar Receiving Lab in Houston. A lot of effort went into doing that. Here you see some of the pictures. So the ventilation system had filters on it, but it was actually laughable, because as soon as the rescue team came to extricate the astronauts, the door of the command module was open, so anything that was in there immediately got out anyway. And here you see what was a biological isolation garment that they wore. Here you see the President Nixon talking to Neil Armstrong, Mike Collins, and Buzz Aldrin. When they were brought on the Hornet aircraft carrier, they were put in quarantine immediately. Then they were put in a building which was kept at a lower pressure, and quarantined there for 14. So a lot of effort went into this. But all that aside, could hypothetical pathogens enter through a spacesuit? And all you have to do is take a look at this one image, Apollo 12, and look at, again, I showed it before, but look at it now in contrast to see how much stuff is coming out of that spacesuit onto the surface, violating forward and back contamination. So Mars, the chances of life, any kind, viruses, any kind, are much, much greater than they are in the moon. So you must design a spacesuit to consider both forward and backward contamination. And what was done, as I mentioned before, it was using bacterial viral filters at the inlet and outlet of the Mars spacesuit. Now you can take that technology and build a suit that can also stop COVID and future pandemics on Earth. So what you see is how you migrate something from a Mars spacesuit to a COVID suit. And it uses filtration, it's lightweight, it has all these requirements, save mass, be cheap, use the environment. And what the main feature of a suit like this is you can't allow anything in, we call it BB, barrier to entry, barrier to exit. And you have to eliminate face-to-face exposure because face-to-face exposure is where most of COVID happens and most of pathogen spreading happens. So the suit that was designed has no openings in the front. You have to be able to get in and out fast in 60 seconds, has to have complete range of mobility, dexterity, fog-free vision, has to be inexpensive. Of course, you're talking about not building a real spacesuit. Reusable, sterilizable, super heavy, lots of stuff go into this. I don't have time to go into all of it. But I did want to show you what the version 1 looks like. It looks like that. And here's a quick, this is status of all this. The suits are basically being tested and developed right now. And before I get to questions, I just wanted to go through one last thing I wanted to show you. Which will be helpful. And let me find it. Man, is this, what did I do? Yeah. Okay, so. Yeah, let me go here, is that it? Okay, so. This is an introduction at a conference 3 weeks ago. Reach further beyond what you think can. And that's what makes a dream come alive. So to show you how this dream came alive after all of this time, I would like to introduce you to our team, if you guys would be good enough to come on out. Okay, so let me run through some of the things you're about to see. So Elizabeth just put a yellow, what we call SOP, secondary oxygen pack, emergency bottle of air, which is in every spacesuit. There's always an emergency supply. So Elizabeth and Eugene are safety officers. So they're here for safety purposes, right? And the red bottle that you see, if you turn it around, so I don't know if you can all read this, but that red bottle is filled with carbon dioxide. That is the Martian atmosphere, 95% of it. So just to give you an idea, we're not on Mars, so we can't pump the Mars atmosphere into the suit, but we can certainly pressurize the suit with the Mars atmosphere that we brought with us. So if, with that as a starting point, we're going to have Cameron actually take you on an experiment. If you would, Cameron.
So the Mars atmosphere, using a compressor that's typically inside the backpack. The Mars atmosphere is compressed and blown into the suit below the neck dam. You see I have a neck dam. So the suit from the neck down is filled with Mars atmosphere CO2. And the helmet portion is filled from my backpack and oxygen supply. So I breathe 100% oxygen inside the helmet. Helmet pressure is kept slightly higher than suit pressure, preventing.
Oops, stand by, guys. Hopefully it'll pick up again. bad internet connection. I guess it's hung up there. I can send that out later. But you were about to witness a demonstration where the helmet CO2 and torso CO2 were going to be measured with sensors, and then you were going to see a demonstration of the what we call the MQ suit, the mobile quarantine suit that it's based on stopping the next pandemic. So I don't know how long I've been talking, James, but a lot of stuff, obviously, in a short time. So if anybody wants to ask questions, let them rip.
Hey, James. So the first question is from Brian Bartel. He's asking, I guess he met you at the Mars conference, and he was curious what the certification requirements are for these suits, or who sets the certification requirements for them?
Well, that's a really good question. For the MQ suit, the mobile quarantine suit, the certification is by the FDA, and it involves like multiple tests. Some of you seen these labels on different garments that it's been tested for tear resistance and absorption and toxicity. So it's those kinds of tests. The MQ suit is projected to be about a $200 price tag. Reusable, sterilizable, available to anybody, especially at the point of introduction of a new outbreak. The what we call the M33 Mars suit, which has just passed 3 days of testing at low pressure and mid pressure. And when I say low pressure, I mean 1 psi and up to 3 psi. Next test is going to be like 4.2 psi. Pressurizing the torso with CO2 and the helmet with oxygen, or air in this case. And then observing and going through a bunch of exercises, observing the PCO2 level in the helmet. That's gone through that successfully. Right now, certification process from that involves adding components and a life support system. That's going to take a while. We actually are applying for a NIAC grant right now. We have several interested parties to help us because we're going to need a special kind of compressor that's silent, and we'll actually pressurize the Mars torso from the outside. So compressors, composite material compressors are high on the list. The algorithm that you saw before, that's already been designed, a baseline of it. That's got to evolve. We've got to add communication. We've got to add the rebreather, oxygen rebreather system. Various things like that are going to take a while. We've targeted 2 to 3 years to finish all those components in what we call CDR, critical design review. Once we have a critical design review, we then enter in the certification process. Involves testing in the environment that's intended to be used in. So that would mean taking that suit, putting it in a chamber that reproduces the Mars atmosphere. And also gravity, to the extent gravity is not as important, because we already know with the weight of the suit, the gravity is going to be fine. But you can do different component testing and qualification tests, and all that that takes place usually at NASA. It depends who the user is. If NASA's the end user, they're going to certify it. They're going to take it to the Chamber A, Space Environment Simulation Laboratory at JSC, or other chambers, or specially designed chambers that can duplicate the Mars environment. That's what you have to do to certify it. And then once you do that, you put a couple of astronauts in it also, and that's when it gets its final certification for flight. It's a long, expensive project, process. Every spacesuit before it flies has to go through that process. In the base suit that's meant to be worn inside the spacecraft, you can cut out 90% of that stuff because that spacesuit is being used only in an emergency. If you lose pressure in Dragon or Starliner or whatever spacecraft it is, that's when they pressurize to help you. But for the most part, they're not even used. So they're certainly not an EVA suit. So the certification is a lot easier. Component testing, all that stuff comes into play. It's an expensive process, and that's why you need a big player to partner with in order to get it through that. So we have several people in mind and talking to, but right now, our company, Planetary Protech, is single-minded in crossing all the check marks to develop this suit as it goes. So we've demonstrated the separation of the helmet and torso. We're satisfied that component, that functional system works, and that's the biggie because that enables you to cut all the weight and avoid a puncture that will kill you. And it also enables you to do planetary protection. So 3 of the big top ticket items are achieved already. Now the idea is adding the other components. And so we're going down that road of partnership to do that in time. So I hope that's a long answer to your question, but there you go.
Larry, hey, it's James. What advice do you have for our students in terms of going into space-related careers? So you're talking to a group of high school students. What advice do you have as they start their careers? And
the top of the list is find a place that is open to the Hypernet paradigm. The Hypernet paradigm, it can take you to do unimaginably beneficial places. So for instance, what you do in a project is you break the project. I'll repeat it. I won't use the charts, but I'll just talk you through it. You take the project, you break it up into major pieces, and each major piece has a starting point, right? And each major piece has a team. Now the team can be 2 or 3, 6. The team can be 2 or 3 or 6, or it can be multiple universities, or it can be universities partnering with NASA, or it can be universities partnering with industry. It doesn't really matter. We call it a talent pool. You recruit a talent pool for each of the teams which are dedicated to a particular project. Now those teams have to talk to each other because it's an overall project is what's important, not the individual piece. So you have to have a communication tool, a web-based communication tool, right? So doing that, it involves a internet component that you actually talk. So, but here's how it works. You start out with a goal, a series of goals that you establish, a baseline, a starting point, and then you do that starting point. When you finish with that starting point, you give a report, and you give a report so that everybody sees that report, and they all comment on it. And then when the whole thing is finished at the end of a semester, or even in the middle of a semester, you recruit experts to actually evaluate your progress. And they evaluate your progress, and you then take it from there, and you mature your design. So you can do that in the short term, or you can do it in the long term. And the idea is if you find a place that's open to working on it's called project-based learning, instead of just taking math and just taking science, and then just taking biology or whatever else it is, and then you trying to piece that together, this is a far preferable way to go. Now, almost every place these days have these interdisciplinary courses, and you likely will find a school, or you can talk to a teacher or a professor about starting a project like this, whatever you want, and they'll know how to break it up into the pieces and evolve it. But just imagine you start out as a freshman, you don't know anything about this, and then you learn. These design projects are designed for you to come back a second time, and a third time, and a fourth time. It's not limited to one course, one semester. That's the key. So when you come in the next time, you're smart, you've learned, you can now become a team leader instead of a freshman or an introductory person. And as time goes on, if you stick with it, you might actually use this for a master's degree. And the whole time you're doing this, don't forget, you're meeting people in the industry. You're meeting people from NASA, from other experts in the field. You're learning how to make presentations. And so by the time you finish this project, however long you choose to be in it, your skill level has been increased tremendously. Your exposure to the field has been increased. So that's what I would urge you all to look for, because being part of a team is the answer to the question that you just asked. If you really want to excel in the space business, find a niche that you can be part of a team and contribute, and watch a project evolve. I'm not going to tell you to get a pilot's license. I'm not going to tell you to go off and take calculus or differential. I'm not going to tell you any of that stuff, because you're probably having to do it anyway. I am going to tell you to look as hard as you can wherever you go for a place that emphasizes what I call the Hypernet paradigm, and I can distribute to that if anybody wants to know. I think it's key.
Awesome. Thank you so much, Larry. That was really nice, especially for our students as they undertake this program. A lot of those points you made are super relevant in terms of working in a team that they're going to practice here with our program as well this summer. So thank you so much, Larry. We really appreciate your time and your insight, and have a great rest of your day.
You too, and good luck to everybody in your project. I know you'll have a lot of fun, and you'll learn a lot. And keep in mind planetary protection, man. It's overlooked, top of the list. Thanks.
Thank you so much.
Searching for extant life on Mars is a science focus for human exploration. And quite honestly, I think it's going to be the science focus for human exploration. All right. So why is it that I can't advance? So I hit return. Here we go. Okay. Much to maybe everybody's surprise, the only mission that's ever looked for extant life on Mars happened in 1976. This is almost 50 years ago. This was the first time we had ever landed anything successfully on Mars, and this was called the Viking mission. This picture in the middle shows a picture of the young Carl Sagan standing in front of a Viking lander mock-up that was shown in Death Valley, California. Carl Sagan at the time was the most famous scientist on the earth. He was just a media personality, and everybody recognized him. And probably the students here have never heard of such a thing. It's because it's that long ago. So we landed two identical landers. One was at a mid-latitude site. The other was at a high-latitude site. And the landers were a search for life focused mission. There were 3 life detection instruments on each of the lander. They actually had identical payloads. And so there were 3 instruments that were specifically looking for metabolism. And then there was a 4th instrument that was just looking for evidence of organic compounds. So next slide shows a kind of a diagram of the 3 life detection instruments. And all 3 of them, they used slightly different approaches, but all 3 of them were attempting to culture microbes out of the soil. So soil was scooped into a funnel, which then distributed the soil to 3 instruments. And each of them were adding some kind of a nutrient broth, and then looking for changes in the gas composition as a result of microbes in the soil doing something to metabolize the nutrients and reduce them to carbon dioxide generally. And what what was discovered was that the soil, all 3 experiments had a reaction, and the reactions were somewhat like what was predicted if there was life in the soil. In fact, 2 of the 3 instruments, well, all 3 instruments had a reaction. They also had used a control experiment where prior to putting the soil into the instruments, it was heated up to temperatures that were thought to sterilize it. And 2 of the 3 instruments still got a reaction after that heating stage, but the 3rd instrument actually didn't. And its results were fully consistent with biology. However, this 4th instrument, which actually was there to look for bulk organics in the soil, showed no evidence of organics at all. And this was thought to rule out a biological explanation. So that the fact that there were no organics and the fact that the reactions were somewhat Earth-like, but were different in detail from what you would expect from an actual, if you were to do this experiment with soil from your backyard, you would see a slightly different way that the reactions occurred, or actually the time history of the reactions. So it was basically concluded from these experiments that the reactions that were seen were chemical and not biological in nature, and and the thing that really put the nail in the coffin of biology was the fact that there was no organic seen. Well, it turns out that was a false negative. Later missions show organics are present on Mars, but Viking missed them. And it missed them for an important reason, which I'll go into later. But it had to do with a highly oxidizing chemical that was in the soil that was not expected and not understood for another 30 years after the mission. So based on the interpretation of the Viking biology experiments as having been a chemical reaction and the lack of organics being interpreted as there being a very highly oxidizing environment that actually destroys organics and would make it impossible for living things to be on Mars. All the subsequent missions that since Viking, everything after 1976 has been focused on searching for, they say they're searching for life, but what they're really searching for is evidence of past liquid water and potential organic signatures of past life. So currently there are 2 NASA rovers on Mars. They're both exploring ancient lake deposits, and they're looking for organic signatures of past life. That's the 2 rovers are the Curiosity rover and the Perseverance rover. They're actually identical rovers, but they're carrying different payloads. The Perseverance rover was landed in 2020, and its focus is to collect samples to return to Earth. And the logic there is that if you're going to find fossil evidence of life, you're never going to be able to detect it robotically without bringing the samples back to Earth and having them in terrestrial laboratories where you can do much more detailed analysis than you can do with instruments that you can send on a robotic mission. So that's where things are at, and that's where they've stood for the last 45 years. So why is that? So this slide shows what's called a phase diagram. It's the phase diagram of water. So liquid water is needed for life as we know it and as we would expect it to be on Mars. And pure liquid water is only stable in the region on this diagram that's in the center here, the dark gray area. And this point right here is what's known as the triple point. The triple point is the point at which liquid water liquid, gas, and solid meet in the phase diagram. And basically below this point, in pressure and temperature regions that are below this point, you either have solid, which is ice and gas, but you cannot have liquid. And so the problem is that the conditions on Mars, the atmospheric pressure and the temperature, fall in this gray region. So liquid water is possible on Mars, but it's very, very slightly possible because the pressure in the Martian atmosphere is near this triple point, the triple point vapor pressure. So effectively, whenever there is liquid water on Mars, it is boiling, and it is, or it is sublimating very rapidly. So it's very difficult to get liquid water on Mars. So basically, the most likely way, the most likely source of liquid water is ice, and it's only if you can melt it. And in order to melt it, you have to have sufficient energy to melt it. So there are losses, heat losses, that you have to overcome. So you have to have enough energy to overcome those losses. Furthermore, the local pressure has got to exceed this triple point vapor pressure, which is 6 millibars. And that's sort of like 6 millibars is about the average surface pressure of gas on Mars. So basically, that's the problem. Temperatures for pure liquid water have to fall between, so this is 0 centigrade or 273 Kelvin, which is 32 degrees Fahrenheit, and about nearly 280 something, 283 degrees Kelvin. So, basically is only about a 10-degree temperature range where pure liquid water is possible. However, pure liquid water is probably not what you're likely to find on the surface of Mars ever. But what is actually known is that thin films of water can persist in mineral soils down to minus 20 degrees centigrade, which is minus 4 degrees Fahrenheit. And salts on Mars, perchlorate salts in particular, can form salty liquid water at very low temperatures. And this perchlorate salts is going to come up again because this is the salt that may be responsible for the false negative that was seen in the original Viking organic analysis experiment. Okay, so again, my focus here is going to be to talk about where you would search for extant life on Mars and why that is an appropriate goal for human exploration. So there are 4 different potential environments that I'm going to talk about. The first is ground ice, either at mid or high latitudes. Second is salts and brines. The third is caves. And the fourth is deep subsurface liquid water aquifers. And all of those are illustrated in this picture here. So gives you an idea of where, both what they are and where they might occur on Mars. Okay, so ground ice is the first one I'm going to talk about, and quite honestly, it's the one that's getting the most attention at this time. So this is a map from a recent paper by Picot et al., and it's showing the location and depth ground ice across all of Mars. I understand you've already had a lecture that's from the swim team, which has also been mapping the ice on Mars, presence of ice on Mars. What this map shows, the scale here on the right is a color-coded depth map of the depth to the ground ice. So what you can see is that everywhere above about 40 degrees, which is about right here, there's a color that's on this color scale. So what that means is that there's ground ice within a meter of the surface, basically everywhere north of 40 degrees north, and pretty much everywhere south of about 50 degrees south latitude. Now, the big dark black areas here are areas where the method that was used to infer this map, the data products that were used were unavailable because there are these big areas on Mars that are covered with dust. And so that the method didn't work where the black areas are because they're covered with dust. The white squares on this map basically are the places where meteors have hit the surface of Mars in the last couple of decades, where we have had good imaging from an instrument called HiRISE. And HiRISE takes repeated imaging of the surface of Mars and finds places that something hit and suddenly it looks different because white ice has been exposed. And the fact that the ice is white tells you that it's pure ice or nearly pure ice, because if it were not nearly pure, it wouldn't show up as white. So basically you've got, a very large fraction of the surface of Mars, especially the northern hemisphere of Mars, which is the place you're more likely to want to land than the southern hemisphere, primarily because it's lower in elevation. So therefore the atmosphere is thicker and it's just easier to land there. But it's also climatologically a pretty reasonable place at, sort of the 40 degree north latitude area. So this is kind of zooming in to what would be the most reasonable places to land on Mars. What you will see here is the indication right here of here's the Viking lander, one of the two Viking landers. Here's the second of the two Viking landers, actually is right in one of those areas where there's near surface ground ice. And then finally, the third one, this is the Phoenix lander, which actually deliberately landed on ground ice in the northern, essentially above the Arctic Circle. So one question that the scientific community has really been just becoming aware of in the last couple of decades is that the climate on Mars, as you see it today, is not the average climate. It is actually, right now, Mars is in what on Earth you would think of as an ice age. This is a diagram showing the obliquity of Mars over the last 10 million years, starting on the right-hand side and 10 million years going to the left. And in the middle, this dark black area is what happens to obliquity on Earth. So obliquity is basically the tilt of the axis. And on both Earth and Mars, the tilt of the axis changes over time. On Earth, it's changing by about plus or minus 5 degrees. And that 5 degrees is enough to cause the ice ages on Earth. So when you're in the low obliquity period on Earth, you actually have kilometers of ice covering most of the northern hemisphere of the Earth. All of Canada, all of Europe, and much of North America is just completely covered with ice and kilometers thick. So on Mars, however, you see the obliquity going between 15 and almost 50 degrees as you go back in time. And this is the, this up and down here, this is the pace at which this is happening. So we are right now at a point where Mars is at its least hydrologically active that it has been in certainly the last 2 million years, and much less hydrologically active than it is, say, 10 million years ago. So this slide again illustrates what we're talking about. This is now, this is the tilt of the axis of Mars, and this is 5 million years ago, 45 degrees. So, and here the time is going left to right. It's a little bit confusing, but the point is that high latitude areas on Mars, when you go back in time and you get to these higher obliquities, the high latitude areas on Mars have a lot more solar insolation than they're experiencing now, especially the northern hemisphere. There's a lot more solar insolation that's happening. And as a result of that, the ice that's in the polar caps is sublimates, gets into the atmosphere, and is redeposited in other places, like at lower latitudes. And that's how we think this ice is getting down into the mid latitudes. And in fact, it can actually be even more globally distributed. So here's what happens to the surface temperature as you go back in time and you go to higher obliquities. So these are climate models that were actually published in 2005. And what they're showing is the number of days per year that you can form liquid water on the Mars surface. Now, it doesn't mean it will form, but it's able to form in terms of being in the thermodynamic box that allows liquid water to be present. So it's kind of in that sweet spot on the diagram I showed you with the phase diagram of water. So this is where it can form now. So it's basically confined to these mid-latitude locations, 0 to 45 degrees. This is where you can get liquid water formation at the present obliquity. But at 45 degrees obliquity, which occurred 5 to 10 million years ago, the number of days or the times where you can have liquid water formation, the locations where you can have it, are moved poleward. And so at 45 degrees and above to like 60 degrees, there are lots of regions, in fact, most of the northern hemisphere, where you could form liquid water. Now, you can only form it at the surface on the basis of this model. So this is just the surface temperatures. And again, the pressure of the atmosphere. But the point is, it's much, much warmer in the places where there is currently ground ice on Mars. And because it's much warmer, that ice can move around or go into the atmosphere and get redeposited somewhere else. Okay, so this is a diagram showing where all the latitude and longitude locations of all the previous Mars landers. And I'm just showing you this quickly to prepare you for the next slide, which is going to show, let's see. Okay, so the next slide is going to show what happens to the ground ice. And again, it's a modeling study that shows for these different climate conditions or the different obliquity conditions where ground ice can occur, but it's plotting it in terms of the location of these different Mars landers. So Mars 2020, this is the Perseverance lander, Viking 1 and 2, and Phoenix are shown in particular. The next slide. So here you go. So basically, this is the ice table depth. This is the depth to ground ice as a function of time going back for the last 2.5 million years. And what you can see is that the Viking, unfortunately isn't shown here, but Zhurong, which is the Chinese lander or Chinese rover, which is actually on Mars right now, you can see that ground ice at the location of the Zhurong rover, which is the highest latitude other than Phoenix that has been landed recently, is 500,000 years ago, is coming up to within 3 or 4 centimeters of the surface. This is ground ice coming nearly to the surface. And this is a paper by Mike Mellon and Hannah Sizemore that was published this year in 2022. And so they basically looked at once you are heating up this polar ice, where does it go? Where does it get redeposited? And they did the plot for just specific locations. But what you're seeing is that the mid latitudes, because all of these landers, except for the Phoenix lander itself, are at mid latitudes. And mid latitudes, ice is coming very near to the surface as you go back over the last 1,000,000 years. So that is ice that's being deposited. So their model started out with assuming no ice is present, and then they just looked at what happens to the ice that gets sublimated off the polar caps and redeposits. So this is an explanation of where this mid-latitude ice is coming from. Okay, so how might you sample that? It's likely that the mid-latitude ice will be a place that humans will want to land, both to look for life and to get resources, because that ice is an important resource for making rocket fuel to come home, for example. But from a life detection point of view, the way that you could sample that ice is to have a drill, could be mounted on a robotic rover, as you see in this picture, or it could be mounted on a human operated or human carrying rover. So in other words, the place that the humans are going to ride around in, if you've looked at the Mars Direct architecture, there's a rover that humans effectively live in, but it also allows them to travel around. A drill like this could easily be mounted on a rover like that. So this is a Honeybee Robotics 1 meter augering drill. It's being flown on the Viper mission to the moon, which is in preparation to be launched in the next year or two. And this was an experiment that I was part of that was located in the Atacama Desert in Chile. And the drill was mounted on a robotic rover and was drilling and collecting samples and putting them into life detection instruments and doing a life detection experiment in a Mars analog site. This is the Atacama Desert in Chile, the driest place on Earth. So it's Mars-like in the sense of being dry, but it is not Mars-like in the sense of being cold. It's actually a hot desert. Okay, so the next thing I'm going to talk about is salts. The map on the top here is showing a color-coded elevation model of Mars, and the white squares shown here are chloride salt deposits, presumably sodium chloride. And there have been at least 640 such sites identified. The bad news is that they're almost all in the southern highlands. So this is the high latitude regions of Mars. The reason that you might want to look in salt deposits for evidence of life comes from research in the Atacama Desert. And actually my previous slide shows these little things sticking up here over above the surface. These are little pinnacles of salt, actually sodium chloride salt. And this whole area is got about 30 centimeters of sodium chloride salt on its surface. And due to wicking of moisture from the subsurface, some of the salt ends up forming these things that look a little bit like candles. And if you break one of these candles off, you will see that there's a little green thing, or little green line subsurface on them. And that is actually a endolithic cyanobacteria. This is a microbe that makes its living by obtaining water from the humidity in the atmosphere by deliquescence. So deliquescence is a process where salts basically suck water out of the atmosphere when it's at high relative humidity, but not saturated. So there's not dew actually forming on the ground, but the salts are nevertheless sucking water out of the atmosphere. And the microbes are actually able to collect that or live off of it. The other diagram here on the right side shows a salt crystal. Again, this is a sodium chloride, regular table salt kind of crystal. And inside that crystal is what's called a fluid inclusion. So what that means is it's actually a liquid water mini environment inside a salt crystal. And this might only be like 1/4 of an inch across, this salt crystal, or maybe even less. But viable microbes can actually be inside that salt crystal and can live there for up to 100 million years. So this is another kind of environment that might be on the surface of Mars or exposed from something that's impacted and brought this type of environment to the surface from the subsurface. The good news about this, actually, is that these environments can be right at the surface. And you might even find them just by having your boots on the ground and walking around. You might find very small deposits of salt that might actually contain viable microbes. So I wanted to make the tie-in to the ground ice as well here, because there is an important tie-in, and this gets back to the Phoenix lander. This is the only lander that ever deliberately landed on ground ice to sample it, and it actually landed at 68 degrees north, because that was the place that at the time there was high confidence that ground ice would be within 1 meter of the surface, or actually 1/2 meter of the surface. There was no drill on this lander. It had a robotic arm and a scoop, which is very similar to what the Viking mission had. And it was, again, it was designed to sample the ice and to determine was it habitable for life. But a very unusual thing occurred, and it wasn't deliberate. It was an accident that it was learned from an experiment on board that lander that 1% of the soil was this very unusual salt called perchlorate. And this shows its chemical formula. It's got a chlorine, it's got 4 oxygen atoms, and it can hold up to 8 water molecules. So it really, really likes water molecules. So perchlorate was not expected, and there wasn't really an instrument designed to detect it, at least deliberately. The instrument was designed to detect nitrate, which is another important element for life. But the perchlorate turned out to be like 1,000 times more reactive to that instrument than nitrate. So when the soil was measured, it blew it completely off the scale. The measurement was blown completely off the scale. And it was recognized by the developer of the instrument that the only thing that could possibly do that, there wasn't enough nitrate, even if it was 100% nitrate, it wouldn't do that. So, but they recognized that perchlorate would do it. So why is perchlorate important for Mars? Well, first of all, it burns organic carbon. It's a very high oxygen. It's got 4 oxygens there. You heat perchlorate up in the presence of organic carbon and it combusts. And it likely burned the organic carbon from the soil that was put into the Viking instrument that was designed to detect organics, very likely burned that to carbon dioxide. And in fact, the way that instrument worked is you put the soil in and you heated it up gradually. And in that heating stage, carbon dioxide came off. And in fact, that was thought to be absorbed carbon dioxide in the soil, but in fact, it was probably the burning of the organics. The second thing is that perchlorate is antifreeze. It actually can lower the freezing point of water to minus 90 degrees centigrade. That's minus 100 degrees Fahrenheit. And these are typical temperatures that are found in the Mars polar regions today. In fact, there is evidence that at the Phoenix lander, there has been liquid water moving stuff around, but it never gets that warm. Even at high obliquity, it doesn't get warm enough for pure liquid water. But this presence of perchlorate can actually make a huge difference and make the water liquid at typical temperatures even found currently. And then finally, it's very strongly deliquescent. So perchlorate salt crystals become water drops at 80% humidity and they remain liquid down to 20% humidity. So that once that salt pulls the water in, you can actually watch it under a microscope. It will become a big drop. And once that drop forms, it won't sublimate again until the relative humidity is very, very low. So from a biology point of view, this is a potential environment where microbes can get liquid water. But the other thing is perchlorate itself is something that microbes can eat. There's a wide variety of microbes that actually can get their chemical energy from perchlorate. So it's it may be the elixir of life on Mars. This diagram actually is from a Nature Astronomy paper in the last couple of years that shows that this deliquescence on Mars, and it's showing that the top diagram and the bottom diagram are either water activity on the top and temperature on the bottom. So the colors here are showing where deliquescence can occur and the temperature at which it occurs, and the water activity when it occurs. So water activity is it's a kind of a measurement of how available the water is for microbes to actually use it. If the water activity is less than 0.6, it's considered that microbes can't use it. But if it's higher than 0.6, they can. So what you're seeing is the water activity and the temperature where deliquescence can occur on Mars. And it is occurring only at night. And the reason for that is that you have to get the relative humidity high enough for deliquescence to occur. And that relative humidity is only gets high enough at night for the relative humidity to get to be 80% or even up to 100%. And at night on the surface of Mars, it's very, very cold. So, you know, this is temperatures that are like minus 75-ish degrees centigrade. So this is too cold for life as we know it. but life can find a way and maybe can find a way. So the point being is that this can happen, if it's happening at all, it can happen anywhere on the surface of Mars, even today. So again, this salts or salty-like environments are an interesting place or an interesting way or environment in which to search for life. And this is the only environment that is widespread enough that it could be virtually anywhere on the Martian surface. Anywhere, at least that's green here in the bottom diagram. Okay, so the next environment I'm going to talk about is caves. So caves have also been recognized on Mars. They're actually not, they're recognized by essentially being holes in the ground. Skylights, because we were only looking at Mars from orbit. We can only see evidence of caves that you can see if you're looking directly down on them. And so this is what the evidence is. It's places where it looks like a crater, but if you look very carefully in this image, you actually don't see the crater floor. You just see darkness. And primarily where you find these things is in volcanic terrains. So it's assumed that these are lava tube entrances. And the reason that you get these skylights is it's a place where the lava has essentially collapsed. So they tend to be circular, but they actually don't have to be. The skylight can kind of be any shape. But 1,000 such entrances have been mapped on Mars. Mostly are associated with these big volcanic units here, the Tharsis volcanoes. But caves are interesting because they can provide a habitable environment that is warmer and wetter and sheltered from cosmic radiation and ultraviolet radiation at the surface. And they really can be quite deep. And if they are, and if there is water in them, that could be liquid. Of course, we don't know any of that because we haven't explored them. So if you can get into the caves and explore them, what you actually would be looking at or looking for is evidence of mineral deposits that might very well look just like mineral deposits. But if you take them, essentially scrape them off the cave walls, and you look at them with the right instrumentation, and in this case, what we're looking at is a scanning electron micrograph of this little green stalactite. So this is a copper stalactite, and it's probably something like a centimeter long. This is not a big thing. But if you take a little of that and you make a scanning electron microscope image that might be looking at 2 micron, 1 micron sort of resolution, you see this structure that is just not known to any mineralogy. It is some kind of a microbially produced structure. So microbes and minerals work together in cave biology to make structures that are unlike anything that minerals by themselves can make. So that's what you would have to look for. But it takes a lot of figuring out exactly what to sample. Here's another example. This is actually from a lava tube cave, and it's a yellow sort of crystalline structure that's sitting on the lava itself. And again, looking at it through a scanning electron microscope is actually how you would identify that it's a biological material. So it turns out that in order to get into cave entrances and to see if it's even an interesting place to look, you could potentially use these little helicopters that have now been proven to work on Mars and are working on the Perseverance or rode along with the Perseverance rover and are part of that mission. Very important technology for evaluating whether it's worth going into a cave to search for life. But actually getting into the cave and exploring it will very likely require humans. On the left side here, I have a photo from a field experiment I was part of that was performed. It's called the Braille Research Project. It was performed in Northern California in a place called Lava Beds National Monument. And we did put a rover inside a lava tube cave. And we had a heck of a time finding a lava tube cave that was big enough to fit that rover. And I think most caves that I've been in, it's just completely impossible to put a wheeled robot inside a cave. You might be able to do it with a legged robot, and legged robots are becoming feasible now. But many caves are just extraordinarily topologically complex. And the one here on the right is a picture showing people inside a cave in Mexico called the Naica Cave. And these are gigantic gypsum crystals. So these people look like little ants crawling around inside a geode. And that's sort of like what it is like. And many caves are just extraordinarily complex to move around in. So finding the right finding the right cave and the right environment where you can even put people inside is going to be challenging. But if you can get in there and if you can get samples, it very likely the most interesting caves for life are going to be the ones that have had water in them, and those are the ones that are going to have the most complex morphology. So, so there's a challenge for human explorers. Okay, finally, the last of these environments is subsurface water, deep subsurface water. So there have been some papers that have come out in the last couple of years that have shown radar evidence of deep subsurface water, or at least that was what it was interpreted as. This was discovered, this radar evidence was found under the South Polar Cap. And under the South Polar Cap, or under any polar cap, is kind of where you might expect liquid water to occur. Although deep beneath the mid-latitude ice, if that ice is getting melted by any process, you might also find pockets of liquid water. But anyway, so this diagram here on the bottom is the evidence shown in the paper by Laro in Nature in 2021. And it showed these bright, in terms of radar reflectivity, regions under the South Polar Cap. So they were positing that this was liquid water at a depth of like 1.5 kilometers. However, there's been a lot of pushback on this measurement. Other papers have claimed that it's too cold for liquid, even perchlorate brine at that depth. And then other bright radar areas have been found that were at even shallower depths using this same radar data. So the current thinking is that this maybe is not liquid water at all. It could be clays or conductive ice. But nevertheless, evidence of subsurface liquid water is, people are still holding out hope that we will find that on Mars, although we haven't definitively found it yet. But should we find it, how would we get to it? Well, fortunately, our friends at Honeybee Robotics have been developing a small, lightweight drilling system that can drill through, not necessarily rock. I don't know if it's capable of doing that, but it can drill through ice. And they have already demonstrated that they can drill through 110 meters of ice in Greenland in a field campaign in 2020. And here's a picture of it from that Greenland expedition. So again, this is of the scale of equipment that human explorers could definitely have or take with them and deploy and monitor, and it's not exactly the kind of mass of a terrestrial drilling rig, but it is a drill rig that could be part of a human exploration program. So these are techniques, all of which are to get samples. The samples themselves would have to be analyzed, either analyzed on the surface of Mars by, in a laboratory that's part of the human exploration habitat, or they would have to be returned to Earth. My own view is that once you have humans on Mars, the sample analysis will be the easy part. It's actually going to be collecting the samples that will be the hard part. So that's all I've got. Any questions?
Yeah, we have a couple questions here, Dr. Stoker. If Mars can get to 20 degrees Celsius, why isn't the ice melting and creating small ponds or small lakes of liquid water?
So Mars can get to 20 degrees Celsius. I think they might have misinterpreted something. I said minus 20, not plus
minus 20, yeah.
But the surface of Mars does get above the freezing point of water, the surface of Mars. Even at locations in the mid-latitudes where there appears to be ground ice. But the ground ice is not right at the surface. So it turns out that even a very small amount of soil can insulate that ice. And the ice temperature is near the diurnal average. So the diurnal average is much, much colder than the highest temperature experienced during the day. And that's basically the story, that if you have 20 degrees C and you have ice at the surface, it's going to sublimate like mad and it won't be there for very long. And in fact, we see that happen. We see that with when these meteorites hit the surface and white ice is exposed, you can watch it over time disappear. So it sublimates away, or it sublimates until there's enough soil cover that you no longer can see it.
Okay, awesome. Next question is from Brian. What is the chemical reaction for perchlorate to react with organic carbon?
Basically, it's the oxygen. It's kind of like burning wood. The oxygen in the perchlorate, when you heat it up, combusts with the organic molecules, which is the reduced carbon. So it's carbon with hydrogen, and basically that reacts and creates carbon dioxide. So it's exactly what happens when you burn oil, an oil lamp or gasoline in your car engine. It's the same kind of reaction, except the perchlorate is holding the oxygen, but it's holding it relatively weakly. And as it heats up, it's very happy to burn.
Okay. Sharia asks, how would Martian soil or salt samples be stored and transported, such as in special containers? If a sample with live microbes is found, is there a procedure in place of how to keep it alive or how to safely contain it to avoid contamination if it is brought back to Earth?
The answer is no, none of those things are in place. Again, it's the entire issue of how to prevent contamination of Earth once you send humans to Mars. I mean, that's a whole nother topic, but it is the human exploration program as it is currently being conceived has not dealt with this problem. And in fact, my personal view is that life detection experiments are needed before we land humans on the surface of Mars, because if we return those humans to Earth, there is no way to prevent contamination of Earth if there is life on Mars. There just is, I mean, a lot of people will say, A, there's no life on Mars, and B, even if there is life on Mars, there's exchange of material between Earth and Mars, and so Earth is already contaminated with Martian material. But our entire protocol for dealing with samples returned from Mars currently is extremely cautious and is bringing the samples back, and samples are supposed to come back from, they're being collected by the Perseverance rover. And those samples are going through extraordinary measures to contain them so that they cannot contaminate Earth. They are being collected in space and they are being brought to the surface of the Earth where there is no chain of contact between Mars and the samples brought to the surface of the Earth. So they basically go up and are put inside a different spacecraft that hasn't been to Mars, and then that spacecraft brings them back to Earth. None of that has been worked out for human exploration, and can't be, because you can't put humans inside of a container that hasn't been to Mars and then bring them back to Earth. It's just not feasible.
Well, one thing I guess I'd follow up on, so if we did send a human crew today, say magically we're able to do that, you know, if you look at what NASA did after the Apollo astronauts came back from the moon, they quarantined them in a trailer 10 days or so. Is that sort of what, you know, in here? But if we were to launch humans today and they were going to come back, is that the approach we would take? Could be similar to that?
In the 1960s, you could get away with that, but you can't get away with that now. I mean, I've been on the actual ship where the Apollo astronauts were actually contained. They were contained in basically an Airstream trailer that was sitting on the deck of the ship. And their human waste was brought back with them in their return capsule and was immediately pitched overboard into the ocean before they were brought on board. So like somehow the ocean isn't going to get contaminated with the human waste. It was just the protocols that were done during Apollo were laughable in retrospect. And we just have to be more conscientious, and we have to understand what the real risks are. And the real risks, in my view, are not that the humans are going to get sick. If the humans are going to get sick, we will know that when they're on Mars. And if we have sick humans on Mars, I would bet that they don't get brought back to Earth. Because, I mean, look at what happened with when COVID broke out on cruise ships during the start of the COVID epidemic. And no one would let those cruise ships land in their ports. You know, you might feel sorry for those people on the cruise ship, but you're by God not going to let them land in your port. I mean, it's the risk is really not so much do the humans get sick. It's are there bacteria that can grow on Earth, and are those bacteria going to explode when they get into an environment that's much more habitable than the one that they live in on Mars? And if that happens, what does it do to the microbial biosphere on Earth, which is what sort of makes the Earth a habitable place for us? So that, I think, is what the real risk is. And that risk needs to be evaluated.
Right. Yeah, I mean, so it sounds like the right way to do a human return from Mars, would be you'd have to have a facility that's completely prepared to receive them and can deal with a variety of scenarios, right? You think, I mean, could you speculate a little bit on what that might look like if a human crew comes back from Mars, and like how we would set that up?
I think that's way beyond my expertise. I mean, it is the Center for Disease Control has what are called type 4 biological containment facilities to try to keep things like Ebola, samples and deal with testing of samples of that nature. But no one has ever done that on the scale of humans. I can't even imagine what would be required.
Well, it sounds like the team at SpaceX has some work to do to figure this out if they're going to send
right. I don't think SpaceX thinks it's their problem. I mean, really, that they may think they can just bring humans back from Mars and, no one's going to complain, but there really are official treaties and legal procedures that will prevent that.
Mm-hmm.
And those haven't really, there hasn't been a lot of discussion about that, but those nevertheless do exist.
Right. Yep. Sounds like some work to do there to figure all that out. Awesome. Well, thank you so much, Carol, for your time today and your presentation today. It was excellent. We really appreciate you being in our program.
All right. Good luck.
Thank you so much. Have a great rest of your day.
Okay. Bye-bye.
Bye-bye. All right, everyone. That concludes our afternoon lecture today. We'll see you again tomorrow at 2 p.m. Pacific time is the next lecture. And that will be Dr. Stephen Benner, kind of continuing our theme of detecting life on Mars. He'll talk a bit about some of his research. All right, well, we'll see you then. Thank you so much, everyone.